If the idea that the rain falling on your neighborhood might be carrying heavy metals, pesticide residues, and viable fungal spores from the Sahara Desert has you as unsettled as it has me, make sure you hit like and subscribe to Signal Watch so you don't miss a single update as this investigation develops. Drop a comment with where you're watching from and tell me, have you noticed unusual dust haze, orange-tinted skies, or unexplained respiratory symptoms during summer storm seasons? And did any official agency tell you what was actually in the air? If you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You are the reason we can keep chasing stories like this. So thank you for having our back. Now, here is what this investigation covers. The June 2020 Godzilla plume. 25 million tons of Saharan material crossing the Atlantic simultaneously, and what laboratory analysis of what it carried reveals about what fell on American communities. The nucleation mechanism. How dust particles hijack storm systems to become delivery vehicles for a chemical and biological payload that standard rain chemistry monitoring was never designed to detect. The pathogen question. The viable fungal spores, dormant bacteria, and pesticide residues documented in transatlantic dust. What the peer-reviewed literature says about their survivability at altitude and their health consequences on the ground. And the monitoring gap. Why no federal agency has real-time capability to tell a community that the rain falling on them right now is chemically and biologically distinct from ordinary rain, and what that gap costs in public health terms. Now, settle in and let's get into it. On June 19th, 2020, NASA's MODIS satellite instrument captured something over the Atlantic Ocean that atmospheric scientists described, with uncharacteristic informality, as the Godzilla dust event. The images showed a continuous mass of Saharan dust stretching from the west coast of Africa to the Gulf of Mexico, a plume approximately 5,000 kilometers wide at its broadest extent, carrying an estimated 25 million tons of material lofted from the Saharan and Sahelian desert floor and transported by the trade wind system across 4,000 miles of open Atlantic. Dr. Pablo Mendez Campos at the University of Puerto Rico, one of the first researchers to formally characterize the event's scale, described it as the largest transatlantic dust transport episode in at least 50 years of continuous satellite observation. Not in recent memory, not in the modern record, in at least 50 years. The scale of 25 million tons requires context to be comprehensible. A standard freight train locomotive weighs approximately 200 tons. 25 million tons is the equivalent of 125,000 freight train locomotives of material. Suspended in the atmosphere, traveling at the speed of the trade winds, covering an area larger than the continental United States. When it reached the Caribbean, it was not subtle. Visibility in Puerto Rico dropped to less than 2 miles on June 23rd and 24th. The air quality index across Puerto Rico and multiple Caribbean islands reached the very unhealthy to hazardous category, the range in which outdoor activity is formally inadvisable for all population groups, not just sensitive ones. Health advisories went out across 7 U.S. states simultaneously: Florida, Louisiana, Texas, Arkansas, Mississippi, Alabama, and Georgia. All of them elevated particulate matter readings during the same 72-hour window. Emergency departments noticed. Miami-Dade County recorded approximately a 30% increase above baseline in respiratory emergency visits during the peak dust days of the event. Not above the seasonal baseline for summer humidity and pollution. Above the baseline for that specific period in that specific year, 30%, from a dust cloud that had left Africa more than a week earlier. Dr. Hongbin Yu at NASA's Goddard Space Flight Center has spent his career quantifying what the atmosphere moves across the Atlantic. His research has established that even in ordinary years, years without a Godzilla event, approximately 180 million tons of Saharan dust cross the Atlantic annually. That baseline number carries its own remarkable implication: 180 million tons every year, in a good year. The Amazon rainforest receives approximately 27 million tons of the annual transport as mineral fertilizer, a direct physical connection between the world's largest desert and the world's largest rainforest, linked by a river of atmospheric material flowing thousands of feet above the ocean surface. The fertility of the Amazon depends, in part, on the erosion of the Sahara. That is the narrative that most coverage of Saharan dust emphasizes: the fertilizer story, the ecological interdependence story. It is accurate and it is important, but it is also incomplete in ways that this investigation will make precise. Because the same mechanism that carries iron and phosphorus to the Amazon also carries what else was on the desert floor when the dust was lofted. And the desert floor, it turns out, is a considerably more complex source material than the fertilizer narrative suggests. The trend underlying the Godzilla event is what makes this investigation necessary. Analysis of satellite-era dust, data by Ridley and colleagues, published in Geophysical Research Letters in 2022, documents that Saharan dust emission has increased by approximately 15% since the satellite record began in the early 1980s. Not a one-time anomaly. A measured, documented multi-decade directional trend. The desert is emitting more dust, more frequently, into an atmosphere that carries it to the same communities on the same wind systems it has always used. The Godzilla event was the largest expression of a trend, and the trend is not reversing. What was in those 25 million tons? That is the question this investigation is built around. And the answer begins not with what the Sahara sends, but with what the Sahara has become. The public narrative about Saharan dust has been shaped by the Amazon story, the fertilizer story, the ecological balance story, the reassuring story of a planetary system in productive equilibrium. And there is truth in that story. Iron and phosphorus from the Sahara are genuinely important to the Amazon's productivity. The mechanism is real. The scale is significant. But the Sahara that feeds the Amazon is not a clean geological archive of ancient mineral deposits. It is a surface that sits downwind of the Sahel, the semi-arid agricultural belt stretching across Africa south of the Sahara, and that has accumulated in its soils and sediments the full chemical legacy of that region's land use history. Heavy metals from natural geological outcroppings and from mining and smelting operations in North and West Africa. Persistent organic pollutants from decades of agricultural chemical use in the Sahelian farming regions. And a biological community, bacteria, fungi, algae, living in the dust-sized particles of the desert floor's top layer, waiting, in some cases, for conditions that will carry them somewhere new. The mineral fraction of Saharan dust is predominantly quartz, silicon dioxide, along with clay minerals, dilute, kyanite, and smectite. These are the materials the Amazon wants. They carry the phosphorus. They provide the mineral matrix for soil development. And they include iron oxides, the compounds that give Saharan dust its characteristic orange and red color, and that give blood rain its name. This mineral fraction is not inert in the human lung. Silicate particles in the PM2.5 size range. Particles below 2.5 micrometers in diameter, small enough to penetrate through the bronchial tree to the alveoli, cause inflammation in lung tissue through both mechanical and chemical mechanisms. But the mineral fraction is the least alarming component of what the Sahara sends. Dr. Joseph Prospero at the University of Miami's Rosenstiel School of Marine, Atmospheric, and Earth Science has been measuring the heavy metal content of transatlantic dust at his monitoring station in Barbados for decades. The measurements are not theoretical. Lead concentrations in settled dust during heavy event days at the Barbados station have been recorded at up to 32 nanograms per cubic meter. Arsenic, cadmium, mercury, and chromium are all detectable at elevated concentrations during major dust events. Some of these metals have natural geological sources in the Saharan rock that is ground into dust by wind erosion. Others reflect the industrial and mining legacy of North and West African development. Smelting, operations, mining activities, and vehicle emissions that have deposited metals into the regional soils over generations, and that are now being remobilized by wind erosion and carried into the Atlantic transport system. The pesticide component adds a layer that receives essentially no public attention. A study by Garrison and colleagues, published in Environmental Science and Technology in 2006, documented organochlorinate pesticides, including lindane and the metabolites of DDT, in transatlantic dust samples. These are persistent organic pollutants, compounds that do not break down readily in the environment and that accumulate in biological tissue. Their presence in transatlantic dust reflects their persistence in Sahelian agricultural soils, where they were applied in previous decades, and where wind erosion is now remobilizing them into the global atmospheric transport system. The Atlantic is not just carrying Saharan geology, it is carrying Sahelian agricultural history. And then there is the biological fraction. Dr. Dale Griffin at the U.S. Geological Survey has published a series of studies beginning in the early 2000s that document something that seems, at first encounter, implausible. Viable microorganisms, living bacteria, and living fungal spores, collected from transatlantic dust samples in the U.S. Virgin Islands. Not dead organisms, not fossil biological material, viable organisms capable of growing in laboratory culture that had completed a journey of more than 4,000 miles across the Atlantic at altitudes where temperatures drop below minus 30 degrees Celsius and UV radiation is intense enough to kill most exposed surface life. The biological fraction is real. It survives. And its identity, when Griffin's laboratory characterized it, raised questions that the public health community has been sitting with uncomfortably ever since. In approximately 1965, Dr. Joseph Prospero set up an air sampler on the island of Barbados. It was not a complicated instrument, a high-volume pump drawing air through a filter. The filter analyzed at intervals for mineral dust content. But Prospero kept it running, year after year, decade after decade, through changes in funding and institutional homes, and the evolution of the satellite era, the Barbados station kept sampling. Today, it represents something unique in atmospheric science. More than 60 years of continuous ground-level measurement of transatlantic dust at a single point in the Atlantic basin. No other station in the world provides a record of this length for this phenomenon. What 60 years of continuous measurement reveals about the long-term behavior of transatlantic dust transport is more informative than any single extreme event analysis. The record has structure, it has a story, and the story is not the comfortable story of a stable, cyclical, natural phenomenon operating in benign equilibrium. The peak period in the Barbados record runs from approximately 1970 to 1987. During this period, dust concentrations at Barbados were approximately 3 to 4 times higher than the pre-monitoring era baseline, extrapolated from the record's early years. This peak coincides precisely with the severe Sahelian drought, the multi-year precipitation failure that devastated the agricultural economies of Senegal, Mali, Niger, Chad, and Sudan across the 1970s and early 1980s. Sahel rainfall declined by approximately 25% between the 1950s and the 1980s. The consequence on the ground was the death of vegetation across millions of square kilometers of the Sahel's southern fringe, the transition zone between savanna and desert. Bare soil exposed to the same wind systems that had previously been stabilized by grass and shrub cover. The dust source area expanded dramatically, the volume of loftable material increased dramatically, and the Barbados record captured the result in real time. Prospero and Patrick Lamb published the formal analysis of this relationship in Science in 2003, a landmark paper establishing the direct quantitative connection between Sahel drought and transatlantic dust transport. Their analysis showed that the variance in Barbados dust concentration was dominated by variability in Sahel rainfall. When it rained in the Sahel, the vegetation cover stabilized, dust emission fell, and the Atlantic received less material. When the Sahel dried out, the reverse cascade unfolded. The Atlantic's dust burden is, in a real and measurable sense, a precipitation gauge for a region of Africa 4,000 miles away. The Sahel drought partially relented from approximately 1990 onward. West African monsoon rainfall partially recovered, and the Barbados record shows the consequence. Dust concentrations declined from their peak, but they did not return to pre-drought levels. The vegetation recovery in the Sahel has been incomplete. Degraded soils recover more slowly than degraded rainfall, and decades of land use pressure have left the Sahel in a permanently altered state relative to its pre-drought condition. And in the most recent decade, the trend has turned upward again. Analysis by Ridley and colleagues using satellite data from 2003 to 2020 documents a renewed increase in North African dust emission that is not fully explained by Sahel rainfall variability alone. Changes in the West African monsoon circulation, land degradation beyond the original Sahelian drought zone, and possibly interactions with large-scale atmospheric circulation changes are all implicated. The Godzilla event of 2020 occurred against this backdrop, a background of already elevated dust transport, compared to the relatively lower levels of the 2000 to 2015 period, on top of which the extreme event was the largest spike in 50 years of records. The Barbados station tells us where the trend has been and where it is now. The dust reaching the Atlantic is not declining toward a historical baseline. It is elevated, and the most recent analysis suggests it is increasing. The question that follows from that finding is not meteorological. It is chemical and biological, because more dust means more of everything the dust carries, the metals, the pesticides, the organisms, arriving on the same Atlantic wind systems at the same U.S. coastlines, intersecting the same storm fronts. Under normal circumstances, if a Saharan dust plume crosses the Atlantic without encountering significant precipitation, the dust arrives as a dry deposition event. It settles slowly over a wide geographic area. Concentrations at any given point are relatively low. The particles disperse. The hazard is real, but distributed over enough area that ambient monitoring stations can detect it and, in principle, issue air quality advisories. This is the scenario that the existing monitoring infrastructure was built around. It is not the worst scenario. The worst scenario is rain, when a Saharan dust plume intersects a weather front, when the dust-laden Saharan air layer encounters the moisture and dynamics of a mid-latitude storm system. Something fundamental changes about how the dust's chemical and biological payload reaches the surface. Instead of settling slowly and dispersing, it falls rapidly and concentrates. The mechanism is nucleation, and it is one of the most important processes in atmospheric science. Cloud formation requires a surface for water vapor to condense onto. Pure water vapor in a clean atmosphere does not spontaneously form cloud droplets. It requires a condensation nucleus, a particle surface onto which the first water molecules can adsorb and around which a droplet can grow. The efficiency of different particle types as cloud condensation nuclei varies enormously. Sea salt is efficient. Industrial sulfate particles are efficient. And Saharan dust, specifically the clay minerals that constitute a significant fraction of Saharan dust, is among the most efficient cloud condensation nuclei and ice nuclei in the atmosphere. A paper published in Nature in 2013 by Atkinson and colleagues established precisely how efficient. Clay minerals in Saharan dust, particularly elite and kaolinite, nucleate ice at temperatures as warm as minus 15 degrees Celsius. Most other aerosol particles require temperatures below minus 35 or minus 40 degrees Celsius to nucleate ice. Minus 15 degrees Celsius is a temperature routinely reached in the middle levels of convective storm systems, the kind of systems that produce rain over the Gulf Coast and the southeastern United States throughout the summer season. Saharan dust particles, when present in sufficient concentrations in the mid-levels of a developing storm, initiate ice crystal formation at altitudes and temperatures where that formation would not otherwise occur. They change the precipitation physics of the storm from the inside. This has consequences for the storm's precipitation output, consequences that are still being actively researched, but it has more immediate consequences for precipitation chemistry, because a raindrop that nucleates on a Saharan dust particle begins its existence already carrying the dust particle's chemical payload. And then, as it falls through the atmospheric column toward the surface, it sweeps additional particles from the surrounding air in a process called below-cloud scavenging. A raindrop falling through 1 kilometer of dust-laden air encounters and incorporates a significant fraction of the particles in its fall path. By the time it reaches the ground, it has collected and concentrated the chemical and biological material from the entire atmospheric column it traversed. Dr. Ana Avila at the Spanish National Research Council has spent decades characterizing the precipitation chemistry of Saharan dust intrusion events in Catalonia and across the Iberian Peninsula. Spain is, after the Canary Islands, the most intensively studied Saharan dust deposition zone in Europe, receiving multiple significant intrusion events per year. Avila's measurements establish the chemical signature of what the Spanish call lluvias de barro, mud rains, with precision, pH values as low as 4.5 to 5, compared to the background precipitation, the pH of approximately 5.6 in clean conditions. Iron concentrations in the orange-brown precipitation measuring 10 to 100 times background levels, and detectable concentrations of lead, arsenic, and copper elevated above what industrial pollution alone would produce in the region. Dr. Cécile Guilleux at the Laboratoire d'Océanographie de Villefranche has extended this work to the broader Mediterranean, documenting in the Journal of Geophysical Research the metal deposition rates associated with Saharan dust rain events across the region. Her measurements confirm what the nucleation of physics predicts. Wet deposition during dust intrusion events delivers metals to the surface at rates far higher than the same material would deliver through dry deposition, because the concentration mechanism of rainfall chemistry amplifies the dose at the point of ground contact. The rain is not diluting the dust, the rain is concentrating it, and in Florida, in Louisiana, in the Gulf states, in the same communities where the Godzilla plume arrived overhead in the summer of 2020, the summer convective storms that produced the region's rainfall were drawing that dust out of the Saharan air layer and delivering it to the surface in every afternoon thunderstorm. Not as a visible orange tide, as rain that looked like rain, rain that people stood in, that ran off roofs into water barrels, that irrigated gardens, that children played in. Rain that was chemically and biologically distinct from ordinary rain in ways that no monitoring system in the United States was measuring in real time. The dust that leaves the Saharan floor and the dust that arrives on the American coastline 4,000 miles later are not the same material. Not chemically, not in terms of their surface properties, their solubility, or their capacity to cause damage in biological tissue. The transatlantic crossing is not a passive transit. It is a multi-day journey through one of the most chemically active environments on Earth, and the dust is transformed by it in ways that the public health discussion of Saharan dust events has been slow to fully incorporate. The transformation begins with iron. Saharan dust is rich in iron oxides, the compounds that give it its characteristic orange and red color and that give the blood rain its name. In the freshly emitted dust, this iron is largely in an insoluble form. The iron is there, but it is locked into mineral crystal structures that do not readily dissolve in water, do not readily enter biological cells, and do not readily participate in the oxidative chemistry that causes cellular damage. The iron solubility of freshly emitted Saharan dust is typically in the range of approximately 0.1 to 0.5%. Nearly all of the iron is bound in insoluble mineral forms. During the transatlantic crossing, that changes. Baker and Jickles, publishing in Global Biogeochemical Cycles in 2006, established that atmospheric processing during transit increases the soluble fraction of iron in Saharan dust to between 5 and 10% by the time it reaches the open Atlantic and begins deposition. A 20-fold increase in soluble iron. The mechanism involves acid processing, sulfuric and nitric acid present in the marine atmosphere, from industrial emissions and natural sources dissolves the carbonate coatings on dust particles, exposing reactive iron oxide surfaces and converting a fraction of the insoluble iron to soluble forms that can enter biological systems. Soluble iron is a different hazard than insoluble iron. In ocean surface waters, the soluble iron arriving in transatlantic dust is a fertilizer. It drives phytoplankton blooms in iron-limited ocean regions, and this is part of the legitimate ecological service that dust transport provides. But in lung tissue, soluble iron participates in a reaction, the Fenton reaction, that generates hydroxyl radicals from hydrogen peroxide. Hydroxyl radicals are among the most reactive oxygen species in biochemistry. They attack DNA, proteins, and lipid membranes indiscriminately, triggering the inflammatory cascade that underpins dust-associated lung disease. The 20-fold increase in iron solubility during transit is not just relevant to ocean fertilization. It is directly relevant to what happens in the lungs of people breathing the deposited aerosol. Dr. Vicky Gracian at the University of California, San Diego, has built a research program around the surface chemistry of mineral dust aerosols in the atmosphere. Her laboratory work, conducted with the rigor of physical chemistry rather than the epidemiological inference that characterizes most health effects research, has established the molecular level mechanisms by which transit alters dust surface chemistry. One of the most significant findings involves photoprocessing, the chemical changes driven by solar UV radiation during the multi-day transit. Rubasing-Higgs and Gracian, publishing in Chemical Communications in 2013, demonstrated that Saharan dust particles exposed to simulated solar UV radiation generate reactive oxygen species at significantly higher rates than unprocessed dust of the same mineral composition. The UV exposure breaks down organic coatings on dust particles and drives photochemical reactions that create surface radical sites, locations on the particle surface that react vigorously with biological molecules on contact. Photoprocessed dust is not just dusty, it is chemically activated in a way that unprocessed dust is not. This matters for the health story in a way that the standard framing of dust events, measured in micrograms per cubic meter of PM2.5 compared against EPA thresholds, does not capture. Two samples of air with identical PM2.5 concentrations can have very different health implications, depending on the chemistry of the particles that make up that mass. A PM2.5 reading from industrial sulfate aerosol and a PM2F reading from photoprocessed transatlantic dust are the same number in the monitoring database. They are not the same health hazard. The monitoring system that treats them as equivalent is operating with a significant blind spot. The pollutant adsorption dimension adds another layer of complexity. As the dust transits the Atlantic, it passes through the marine boundary layer, the lower atmosphere above the ocean surface, where industrial emissions from Europe and North America have elevated concentrations of sulfate, nitrate, and organic compounds above background levels. Dust particles, with their large surface area per unit mass, adsorb these compounds efficiently. By the time a dust particle completes the transatlantic crossing, its surface chemistry reflects not just the Saharan geological source, but the entire atmospheric chemistry of the transport pathway. A composite aerosol that carries European industrial pollution adsorbed onto Saharan mineral dust, arriving on American soil as a package that no single source characterization adequately describes. The picture that emerges from Gracian's surface chemistry work, Baker and Jekyll's iron solubility measurements, and Rubasing-Higgs' photoprocessing experiments is consistent. Transatlantic Saharan dust is more soluble, more reactive, and more capable of generating oxidative stress in biological tissue than the source material that left the desert floor. The crossing makes it worse, and when it arrives in rain, the concentration mechanism that nucleation and below cloud scavenging provide delivers it to surfaces, to skin, to soil, to water, at doses that dry deposition does not. The atmosphere is not sterile. That sentence, stated plainly, seems obvious. Of course, the air contains microorganisms, But the implications of atmospheric microbiology for long-range dust transport are not fully internalized in the public health infrastructure that is supposed to protect people from airborne hazards, because the infrastructure was built around the premise that the relevant airborne biological hazards are locally generated. Hospital ventilation systems are designed around local airborne pathogens. Air quality monitoring networks measure locally generated and transported pollution. The possibility that viable microorganisms could complete a 4,000-mile journey across the Atlantic Ocean, arrive in the precipitation falling on an American community, and cause disease in the people that precipitation contacts is not a scenario that any federal agency has built a monitoring system around. Dr. Dale Griffin at the U.S. Geological Survey has been making the case that this oversight is significant since 2001. Griffin's work began with a straightforward question. When African dust events reach the U.S. Virgin Islands, what is alive in them? He collected air samples on high dust days when satellite imagery confirmed the presence of a transatlantic African dust plume overhead, and on low dust control days. He ran cultures, he sequenced DNA, he characterized what was there. The results were published in a series of papers that represent the foundational literature of atmospheric biological transport across the Atlantic. On high dust days, the samples contained viable bacteria and viable fungal spores, not at trivial concentrations, at concentrations measurably and significantly above the control days. The organisms could be cultured, they were alive, they had made the crossing. Among the fungal species Griffin identified, multiple members of the genus Aspergillus. The Aspergillus group includes organisms with very different health implications. Aspergillus flavus produces aflatoxins, potent carcinogens, and immunosuppressants that are among the most dangerous naturally occurring biological toxins known. Aspergillus fumigatus is an opportunistic pathogen that causes invasive aspergillosis, a severe, life-threatening infection in immunocompromised individuals. Approximately 300,000 cases of invasive aspergillosis occur globally each year, with mortality rates ranging from 30% in patients with treated underlying conditions to 90% in the most severely immunocompromised patients. A. Fumigatus spores are ubiquitous in the environment. The organism is so common that healthy immune systems routinely clear it without incident. The people who die from invasive aspergillosis are the people whose immune systems cannot clear it. Organ transplant recipients on immunosuppression, patients on high-dose corticosteroids, individuals with hematological malignancies. These populations exist in every American community, and Griffin's data shows that A. fumigatus viable spores are arriving in transatlantic dust events. How do they survive? The UV environment at 20,000 feet should be sterilizing. The temperatures are extreme. The journey takes 7 to 14 days. Griffin and Kellogg addressed the survival mechanism directly in a review published in The Lancet in 2006, a choice of journal that is itself significant, given that The Lancet is a clinical medicine publication, not an atmospheric science journal. Their analysis established the UV shielding mechanism. Organisms in the interior of a dense dust plume are physically shielded from UV radiation by the surrounding dust particles. The optical depth of a major Saharan dust plume is sufficient to reduce UV penetration to a fraction of clear sky values at the plume's center. An organism embedded within the plume, not on the exposed surface, but within the mass, experiences UV doses orders of magnitude lower than it would in clear air. The plume is effectively an atmospheric transport vehicle with built-in radiation shielding for its biological cargo. Approximately 60% of culturable bacteria in transatlantic dust samples survive the crossing in Griffin's experiments, a viability rate that is not trivial. These are not organisms present at trace concentrations of marginal significance. They are present in numbers sufficient for culture growth, at concentrations that scale with the intensity of the dust event overhead. A study published in Science of the Total Environment in 2020 by Acosta Martinez and colleagues added a dimension to the biological transport picture that goes beyond species identification. Their analysis of transatlantic dust samples detected antibiotic resistance genes, genetic sequences encoding resistance to multiple classes of antibiotics in the dust material. The source of these genes is almost certainly antibiotic-resistant bacteria whose genetic material, even if the bacteria themselves do not survive intact, arrives in the deposition zone and can potentially transfer resistance genes to susceptible organisms in the soil and water of the receiving environment. Horizontal gene transfer, the mechanism by which antibiotic resistance spreads between bacterial species, is an active process in soil and water environments. Transatlantic dust is delivering the genetic raw material for that process to American soils. The domestic analog that makes Griffin's findings most legible is valley fever. Coccidioides immitis and C. posadaceae, the fungal species that cause coccidioid live in the arid soils of the American Southwest and northern Mexico. When windstorms mobilize dust from those soils, viable coccidioid spores travel with the dust. People who inhale them in sufficient doses develop valley fever, a respiratory illness that ranges from self-limiting flu-like disease in healthy individuals to severe progressive pulmonary disease and fatal dissemination in immunocompromised patients. Valley fever cases in the United States have increased dramatically over the last 2 decades, tracking the combination of drought, dust storm frequency, and human population expansion into the endemic zone. It is the established American model for fungal pathogen transport by dust-driven aerosolization. Griffin's transatlantic work asked the direct question, is there an Atlantic analog to valley fever? Are Saharan fungal pathogens completing the crossing and depositing viable spores in regions of the United States where they have no established ecological presence and where physicians may not consider them in differential diagnoses? The answer from the laboratory data is that viable fungal spores are making the crossing. The epidemiological evidence to connect those laboratory findings to clinical disease outcomes in the U.S. has not been systematically sought, because there is no monitoring program designed to find it. The peer-reviewed literature on the health consequences of Saharan dust events is concentrated in 2 geographic zones, the Canary Islands and the Iberian Peninsula. Not because the dust falls only there, but because those regions have the combination of frequent, intense exposure and sustained scientific attention that produces a usable epidemiological record. The Canary Islands sit approximately 100 kilometers off the northwest coast of Africa, directly in the path of the most intense Saharan dust outflows. The islands experience significant dust events multiple times per year. Their population is large enough for epidemiological analysis, and Spanish environmental and public health researchers have been studying the health consequences of these events for decades. The foundational U.S. applicable findings from that literature are specific enough to be useful. Perez and colleagues, publishing in Occupational and Environmental Medicine in 2008, analyzed emergency department visits across the Canary Islands over a multi-year period, stratifying by dust concentration levels measured at the Canary Islands Air Quality Monitoring Network. Their finding, on high dust days, emergency department visits for respiratory disease increased by approximately 8 to 12% above the low dust baseline. Not a marginal signal. 8 to 12% more people seeking emergency care for breathing problems, driven by a change in the composition of the air, not by any change in the local pollution sources they were used to. The cardiovascular signal is present too. Jimenez and colleagues, publishing in Environmental Health in 2010, examined all-cause and cause-specific mortality in Madrid during periods of Saharan dust intrusion. Their analysis documented elevated mortality on dust days, with a 24-hour lag between peak dust concentration and peak mortality signal, the characteristic lag of acute cardiorespiratory events. The effect was strongest for cardiovascular causes, which might seem counterintuitive for a primarily respiratory hazard. The mechanism is the systemic inflammatory response. PM2.5 particles that reach the alveoli trigger local inflammation that produces cytokines, inflammatory signaling molecules, that enter the circulation and affect cardiovascular physiology. fine particle air pollution's cardiovascular effects are among the most robustly documented findings in environmental epidemiology. Saharan dust events drive fine particle concentrations up, and the cardiovascular consequences follow. The U.S. record is thinner but present. Rice and colleagues, publishing in Environmental Health Perspectives in 2013, examined hospital admissions in the southeastern United States on days when satellite data confirmed significant African dust transport overhead, compared to control days of similar meteorological conditions without African dust. Their analysis found significantly elevated asthma-related admissions on high African dust days. The signal was not as clean as the Canary Islands data. The southeastern United States receives African dust against a background of domestic air pollution that complicates the attribution, but it was statistically significant and directionally consistent with the European findings. The vulnerability distribution in the health record follows a predictable pattern. Children's lungs are still developing, the alveolar surface area expands dramatically during childhood, and fine particle exposure during development has documented effects on lung function growth trajectories that can result in permanently reduced lung capacity by adulthood. Studies of children in high dust regions of the Canary Islands document measurable differences in spirometry outcomes, the lung function tests used to assess respiratory health, between high dust and low dust residential environments. The elderly face a different but equally serious compound vulnerability. Baseline cardiovascular and respiratory disease reduces the physiological reserve available to manage the acute inflammatory stress of dust exposure, and the medications that manage chronic cardiovascular disease can interact with the oxidative stress induced by particle exposure in ways that compound rather than buffer the effect. What the epidemiological record does not yet contain, and this is the critical gap that connects the health literature to the monitoring gap this investigation will document, is any systematic analysis of health outcomes, specifically associated with the wet deposition pathway. The studies above are built on dry deposition events, dust in the air, measured at PM2.5 monitoring stations, correlated with hospital data. The wet deposition pathway, where dust arrives, concentrated in precipitation, delivered to skin and surfaces at doses that the dry deposition pathway does not achieve, has not been studied in the U.S. context because there is no monitoring infrastructure to characterize what is in precipitation on a storm-by-storm basis in real time. The health literature documents the hazard of breathing the air during dust events, the hazard of standing in the rain or gardening after it, or drinking from a rainwater collection system during the days following a dust-rain intersection has not been systematically quantified. The signal that does exist is alarming enough to justify the investigation. The signal that could exist, if the monitoring infrastructure existed to measure the wet deposition pathway, might be considerably more alarming than what the current literature can document. The Saharan air layer is one of the most studied features of the tropical Atlantic atmosphere, primarily because of its role in hurricane dynamics. NOAA's Hurricane Research Division has been tracking it for decades, not out of concern for dust chemistry, but because the SAL's warm, dry air is the most significant environmental control on tropical cyclone development in the main development region of the Atlantic Basin. The SAL forms over the Sahara when daytime heating drives intense convection over the desert surface, lofting dust-laden air into the mid-troposphere. This elevated layer, typically occupying altitudes between approximately 5,000 and 15,000 feet, is carried westward by the trade wind system, overriding the moist, unstable marine boundary layer air that tropical cyclones need to develop and intensify. When the SAL overrides a developing tropical disturbance, it injects warm, dry air into the storm circulation, suppresses the deep convection that powers tropical cyclone intensification, and increases the vertical wind shear that tears apart organized circulation. Dr. Jason Dunyan at NOAA and the University of Miami's Cooperative Institute for Marine and Atmospheric Studies has published extensively on the sail's role as a natural hurricane suppressor. In years of heavy Saharan dust transport, the suppression effect is stronger, and the Atlantic hurricane season is statistically less active. That is the story NOAA tells about the SAL. It is an important and accurate story, but it is the story of what the SAL does to tropical systems, the storm systems that develop over the warm, open Atlantic. It is a different story from what the SAL does when it reaches the North American coastline and encounters the mid-latitude frontal systems and convective storms that produce rainfall over the Gulf states, the Southeast, and the mid-Atlantic. And that second story is the one that matters for the precipitation chemistry investigation. When the SAL reaches the U.S. coastline in summer, it encounters a different atmospheric regime than the tropical Atlantic. Mid-latitude frontal boundaries, mesoscale convective systems, and sea breeze-driven afternoon convection over the Florida Peninsula and Gulf Coast all provide mechanisms for drawing SAL air down from its elevated transport layer into the lower troposphere, where it can interact with developing precipitation. The warm, dry SAL air, when it descends into a convective environment, provides additional convective inhibition that can suppress rainfall development during the day. And then, when the convective inhibition breaks and storms do develop, provides a reservoir of dust-laden mid-level air that the convective updraft draws through. In July 2020, following the peak of the Godzilla Plume's passage across the Atlantic and over the Gulf of Mexico, precipitation chemistry sampling at the University of Florida in Gainesville documented iron concentrations in rainwater at approximately 40 times the background level. The water standing on surfaces after rain events that showed brown-orange discoloration consistent with iron oxide deposition, visible confirmation of what the chemistry was measuring. The Florida Department of Environmental Protection's field notes from this period document the visual and chemical signal clearly. Iron at 40 times background is not an artifact of measurement uncertainty. It is a specific, quantified chemical fingerprint of Saharan material arriving in precipitation. This is not a new phenomenon in the documented European experience. Spain records approximately 3 to 5 significant blood rain events per year. Precipitation events visibly colored by Saharan dust content, with the chemical signatures that Avila and colleagues have characterized across decades of sampling. The Canary Islands record them more frequently. The UK has documented them on multiple occasions, most recently in February 2022, when orange-tinted rain fell across parts of England and Wales during a Saharan intrusion event that British meteorological media covered with appropriate surprise and insufficient chemical detail. The U.S. lacks the monitoring infrastructure to know how frequently this happens on American soil. The National Atmospheric Deposition Program maintains approximately 100 sampling sites across the contiguous United States that measure precipitation chemistry, but using weekly composite samples. A single storm event on a Tuesday that carries 40 times background iron levels is diluted into a week's worth of precipitation chemistry before the sample is analyzed. The individual storm signal is lost in the average. The 80 stations with any precipitation chemistry capability at all, and their weekly sampling frequency, were designed to track the slow trends in acid rain chemistry from industrial sulfur emissions. They were not designed to resolve the event-scale chemistry of dust-contaminated precipitation events. The monitoring infrastructure and the phenomenon it should be monitoring are mismatched by design, built for a different problem, deployed against a different baseline. The epidemiological literature is built on populations and statistics. It tells you that respiratory emergency visits increase by 8 to 12% on high dust days. It tells you that all-cause mortality shows a 24-hour lag following dust concentration peaks. It tells you that asthma-related hospital admissions in the southeastern United States are statistically elevated on days of documented African dust transport. These are important findings. They translate real physical hazard into the language that public health policy responds to. They do not tell you about the specific communities that sit in the direct path of transatlantic Saharan dust transport every summer. Communities that do not have the scientific infrastructure of the Canary Islands or the institutional attention of metropolitan Spain. Communities where the baseline health burden from respiratory disease is already high, where the medical infrastructure is already strained, and where the additional load from a transatlantic dust event is absorbed without systematic documentation and without any public communication that would allow residents to understand what is causing their symptoms. Puerto Rico sits at the front line of transatlantic Saharan dust transport, geographically positioned such that every major westward dust transport event passes directly overhead before reaching the continental United States. The Godzilla event's impact on Puerto Rico was documented in real time. AQI readings in the hazardous category, visibility below 2 miles, health advisories issued across the island. What was less visible in the public record is the population that those advisories reached and what their ability to respond to them was. Puerto Rico has among the highest rates of childhood asthma in the United States. Approximately 25% of Puerto Rican children have been diagnosed with asthma, compared to approximately 8% nationally. The elevated prevalence is multifactorial. The island's geography, its historical industrial pollution, housing conditions, and access to health care all contribute. But an island with 25% childhood asthma prevalence, sitting directly in the path of every major Saharan dust transport event, receiving AQI levels in the hazardous category multiple times per summer season, is an island where the dust hazard compounds an existing health burden in a population that is already carrying more than the national average. The Caribbean Basin, more broadly, represents a population of approximately 45 million people who experience elevated Saharan dust exposure on a seasonal basis without the monitoring infrastructure, the clinical awareness, or the public communication systems that would allow them to manage the exposure effectively. During the Godzilla event, health advisories were issued in Puerto Rico, the Dominican Republic, Jamaica, and several other Caribbean nations simultaneously, but the content of those advisories was limited to general guidance about staying indoors and avoiding outdoor exertion. They did not communicate the chemical composition of what was in the air. They did not distinguish between the mineral fraction that drives PM 2.5 readings and the biological fraction that those readings do not capture. They did not address the wet deposition pathway that would follow when the dust plume intersected Caribbean precipitation systems in the days after its passage. On the continental U.S. Gulf Coast, the communities most directly exposed to Saharan dust storm intersection events are concentrated in Florida, Louisiana, and Texas, states with significant elderly populations, significant childhood asthma burden, and, particularly in Louisiana and South Texas, significant poverty concentrations that reduce the capacity to respond to environmental health advisories even when those advisories are issued. The combination of elevated baseline vulnerability and the specific geographic positioning that makes these communities the first continental U.S. populations to encounter arriving dust plumes is not a coincidence. It is the spatial epidemiology of a hazard that follows the trade wind system and the Atlantic coast geography. The absence of systematic data from these communities is not evidence that the hazard is absent. It is evidence that the monitoring infrastructure has not been built where the hazard is concentrated. Epidemiological studies require data. Data requires monitoring. Monitoring requires investment. Investment follows attention, and the attention that Saharan dust events receive in the United States has, until recently, been primarily aesthetic. Photographs of orange haze over Miami, social media posts about the brown sky, meteorological coverage of the Godzilla event's satellite imagery. The health dimensions of what is arriving in those plumes and what falls when those plumes meet a summer storm have not received the institutional attention that would translate into the monitoring investment that would produce the data that the epidemiological literature needs. The Saharan air layer suppresses hurricanes. That is the finding that NOAA and the National Hurricane Center communicate when asked about the SAL's role in the Atlantic system. It is accurate. Years with heavy Saharan dust transport are statistically associated with reduced Atlantic hurricane activity. The mechanism is established. The SAL's warm, dry air and the associated wind shear it imposes on developing tropical systems makes it harder for tropical disturbances to organize into tropical storms and hurricanes in the main development region. But there is a more complex dynamic, operating in the relationship between heavy Saharan dust years and Gulf Coast rainfall chemistry that closes the loop, opened in Part 8, and that the NOAA public communication on the SAL does not address. In years of heavy transatlantic dust transport, the years when the SAL is most active, when the largest plumes are crossing the Atlantic, the suppression effect tends to be strongest during the early and middle portions of the hurricane season, roughly June through August. Dust transport peaks in summer, driven by the atmospheric dynamics of the West African heat low. During this period, the Gulf Coast and southeastern United States are receiving frequent convective precipitation. The afternoon thunderstorms and mesoscale convective systems that produce the majority of summer rainfall in these regions. These are precisely the storms that interact with SAL air, the dust-laden mid-level air that is suppressing tropical cyclone development over the open Atlantic is the same air mass that is overriding the Gulf Coast and southeastern U.S. during the convective season. When afternoon thunderstorms develop over Florida, Louisiana, and the Gulf states in June and July, they are developing in an environment where the mid-levels of the atmosphere, the 5,000 to 15,000 foot layer where convective updrafts draw their air from, carry Saharan dust concentrations that can be orders of magnitude above background in years like 2020. Dr. Jason Dunyan's research on SAL structure and dynamics has documented that SAL intrusions over the Gulf of Mexico can be as dust dense as the SAL over the open Atlantic. The material has not been fully deposited by the time it reaches the Gulf. The convective storms that develop under and through this dust-laden layer are the storms that produce Gulf Coast summer rainfall. They are drawing Saharan dust through their updrafts, incorporating it into their precipitation physics, and delivering it to the surface in every afternoon rainstorm across a region spanning from Pensacola to Corpus Christi. The compound relationship here is not additive, but interactive. In a year of heavy Saharan dust transport, the hurricane season is suppressed, reducing the attention and meteorological infrastructure devoted to tracking the plume's progress across the Atlantic. Simultaneously, the Gulf Coast convective season is proceeding through a dust-laden mid-level atmosphere, with no monitoring system for the resulting precipitation chemistry. And the communities that would be the focus of hurricane preparedness attention are instead receiving repeated dust-contaminated convective rainfall events that go entirely unmeasured and unreported. The suppression of hurricane activity in heavy dust years is not the good news it is sometimes presented as. A Gulf Coast community that does not face a major hurricane in a heavy dust year is a community that instead faces months of contaminated summer rainfall from convective systems drawing through a dust-laden atmosphere, an event that generates no emergency management response, no federal disaster preparation, no public health advisory infrastructure, and no systematic chemical monitoring of what is falling. The National Oceanic and Atmospheric Administration tracks the SAL with impressive precision for the purpose of hurricane forecasting. The NOAA reconnaissance aircraft that fly through developing Atlantic storms carry instruments that characterize the SAL's temperature and moisture structure in detail. None of those instruments are tasked with characterizing the SAL's dust chemistry, its metal content, its biological load, its pesticide residues. The SAL is intensively monitored as a meteorological feature. It is essentially unmonitored as a chemical and biological transport mechanism. Federal environmental monitoring in the United States is organized around sources, not transport pathways. The Clean Air Act's Ambient Air Quality Monitoring Network, the SLAMS network, operated by state environmental agencies with federal oversight, was designed to measure the air quality consequences of domestic pollution sources, power plants, industrial facilities, vehicles, and the secondary chemistry their emissions drive. The monitoring stations are located where the sources are. Their sampling protocols are calibrated to the pollutants those sources produce. They measure PM 2.5 as a mass concentration, micrograms of particles per cubic meter of air, without distinguishing between the wildly different chemical compositions of particles that contribute to that mass. A PM 2.5 reading of 35 micrograms per cubic meter from industrial sulfate aerosol, and a PM 2.5 reading of 35 micrograms per cubic meter from transatlantic Saharan dust, carrying viable Aspergillus spores, photoprocessed iron oxides, organochlorine pesticide residues, and antibiotic resistance genes are the same number in the Federal Air Quality Monitoring Database. They trigger the same alert category. They are communicated to the public with the same guidance. Sensitive groups should reduce outdoor exertion. They are not the same hazard. The National Atmospheric Deposition Program, which monitors precipitation chemistry across the United States, represents the monitoring system most relevant to the wet deposition pathway. NADP operates approximately 100 sampling sites nationally, collecting weekly composite precipitation samples that are analyzed for a suite of chemical parameters, including pH, sulfate, nitrate, ammonium, and a handful of trace metals at a subset of sites. The program was designed in the 1970s and 1980s to track the acid rain problem, the sulfate and nitrate deposition from coal combustion and vehicle emissions that was acidifying lakes and damaging forests in the northeastern United States and Canada. It has served that purpose well. It was not designed for and is not capable of providing real-time event scale monitoring of precipitation chemistry during dust-contaminated storm events. The specific technical gaps are each individually significant. The sampling frequency, weekly composite samples, means that an individual storm event's chemistry is averaged into a week's worth of precipitation before analysis. The storm that brings 40 times background, iron concentration on a Tuesday, is invisible in the weekly composite. The biological component, the viable fungal spores and bacteria documented by Griffin, is not a parameter in NADP's analytical suite. No federal precipitation monitoring program tests rain samples for viable microorganisms. The spatial density, approximately 100 stations nationally, covering 3.8 million square miles, means that many regions with documented Saharan dust exposure have no precipitation chemistry monitoring at all. The EPA's Air Quality Monitoring Network has no protocol for Saharan dust events that distinguishes them from domestic pollution events in real time. There is no federal alert category for dust-contaminated precipitation expected. No system that would communicate to communities that the afternoon thunderstorms forecast for their area are expected to fall through a Saharan dust layer and deliver chemically and biologically complex precipitation. The National Weather Service issues air quality alerts based on PM 2.5 and ozone readings. It does not issue precipitation chemistry alerts. There is no regulatory framework for precipitation chemistry alerts in the United States. Dr. Joseph Prospero, in interviews over many years of advocacy for improved monitoring, has been consistently specific about what a meaningful monitoring upgrade would require. A network of high-frequency precipitation chemistry samplers capable of resolving individual storm events cited in the regions of highest Saharan dust exposure, the Caribbean, Florida, the Gulf Coast, with analytical capacity for the biological fraction in addition to the standard chemical parameters. The technology exists. The analytical methods exist. The scientific justification exists in 2 decades of peer-reviewed literature. The monitoring network does not exist because the regulatory and public health frameworks that would fund it treat Saharan dust as an air quality curiosity rather than a compound chemical and biological hazard requiring dedicated surveillance. The monitoring gap is not a technical failure. It is a prioritization failure, a consequence of institutions designed to manage the hazards of the industrial era encountering a natural transport phenomenon that delivers a complex, variable, and partly biological payload through a pathway their monitoring architecture was not built to detect. The result is that communities in the path of every major transatlantic dust event are exposed to a hazard whose real-time chemistry is unknown to any government agency and unknown to them. Before moving to the investigation's assessment, address something directly. The phenomenon of blood rain, precipitation visibly colored by mineral content, falling from skies that carry the Sahara's iron oxides, has been generating conspiratorial content online with increasing volume since the Godzilla event of 2020 made it visually undeniable to millions of people who photographed orange haze over Florida and the Gulf Coast. The explanations circulating in that content ecosystem range from chemtrails to deliberate pathogen deployment to HARP-driven atmospheric modification. None of them are correct, and addressing why they are wrong is not a defensive gesture. It is the prerequisite for understanding what the real story actually says. The blood rain phenomenon has a documented history that predates every technology invoked in the chemtrail hypothesis by more than 2,000 years. Theophrastus, the Greek philosopher and student of Aristotle, described events of colored rain falling in the Mediterranean world in the 4th century BCE. Medieval European chronicles record multiple episodes of red and brown rain events that were interpreted in their time as supernatural portents. Scientific investigation of these events, beginning in the 19th century with chemical analysis of the deposits, established the Saharan mineral origin of the coloring material. Before atmospheric science was a formal discipline, and before aircraft of any kind existed. The chemistry of blood rain has been characterized with increasing precision since the 1980s in the peer-reviewed literature of European atmospheric chemistry. The phenomenon is as old as the Sahara's dust transport system, which has been operating for millions of years. The HARP argument fails on the same energy arithmetic that defeats it in every other context. HARP's maximum radiated power is approximately 3.6 megawatts, directed into the ionosphere. The thermal convection over the Sahara Desert that lofts 25 million tons of dust into the mid-troposphere in a single event is powered by the radiative energy of the sun, absorbed by approximately 9 million square kilometers of desert surface, an energy flux on the order of 10 to the 21st watts. The ratio of HARP's output to the energy driving a major Saharan dust event is approximately 300 trillion to 1. This is not a close comparison. It is a statement of physical impossibility rendered in arithmetic. The deliberate pathogen deployment hypothesis fails on the organisms identified. Griffin's Aspergillus species are ubiquitous in Saharan and Sahelian soils. They are exactly the organisms you would expect to find in dust from that region. Exactly the organisms that ecological surveys of North African desert soils have identified for decades. Their presence in transatlantic dust is precisely consistent with the hypothesis that dust from that region carries its native microbial community, and precisely inconsistent with the hypothesis that they were introduced by any external agent. The antibiotic resistance genes documented by Acosta-Martinez are consistent with the known distribution of antibiotic resistance in African agricultural soils, where antibiotic use in livestock farming has driven the same resistance evolution documented on every continent. They are not the signature of a weapons program. They are the signature of a global agricultural system. The real human fingerprint in this story requires no conspiracy framing to be alarming. The Sahel's land degradation, the expansion of the dust source area through overgrazing, deforestation, and agricultural intensification that has continued for decades is a human-caused change with human policy consequences that has measurably increased the volume of material entering the Atlantic transport system. The absence of a monitoring network for transatlantic dust chemistry in the United States is a policy failure with real public health consequences. The failure to incorporate biological transport into the public health frameworks governing air quality monitoring is an institutional gap with a documented price in increased respiratory hospitalizations. The advice to stay indoors during high dust air quality events, advice that is issued without any communication of the biological fraction of what is in the air, is guidance calibrated for an industrial pollution paradigm that does not adequately describe the transatlantic dust hazard. None of that requires a conspiracy. The ordinary atmospheric chemistry and public health policy failure is alarming enough without embellishment. In fact, the conspiracy framing actively obscures the actionable dimension of the story, because if the blood rain is caused by chemtrails, the only response is to demand the program's termination. If it is caused by Saharan dust transport driven by land degradation in the Sahel and arriving in the absence of adequate monitoring infrastructure, the responses are concrete. Restore Sahel vegetation, build the monitoring network, update the analytical frameworks, Communicate the biological fraction of the hazard to the communities in the Plume's path. Conspiracy framing converts an actionable policy problem into an unanswerable accusation. That is not useful to the communities underneath the plume. The EPA's regulatory framework for ambient air quality is built around 6 criteria pollutants: particulate matter, ground level ozone, carbon monoxide, sulfur dioxide, nitrogen dioxide, and lead, established under the Clean Air Act and reviewed on a periodic schedule by the Clean Air Scientific Advisory Committee. The framework has driven enormous improvements in U.S. air quality over the 50-plus years since the Act's passage. Particulate matter concentrations in U.S. cities are a fraction of what they were in the 1970s. Acid rain has been substantially reduced. The framework works for the problem it was designed to solve. The problem it was designed to solve was domestic, industrial, and vehicular pollution. The framework has no category for a transnational, transoceanic aerosol transport event that delivers a chemically and biologically complex payload through the precipitation chemistry pathway. PM 2.5 is PM 2.5 in the regulatory framework, regardless of whether it originated in a coal plant in Ohio or in the Saharan floor, and crossed the Atlantic in a 25 million ton plume. The biological fraction, the viable fungi and bacteria, is not a regulated air pollutant under the Clean Air Act. There is no national ambient air quality standard for Aspergillus fumigatus spore concentrations in ambient air. There is no standard for organochlorine pesticide concentrations in precipitation. There is no standard for antibiotic resistance gene deposition rates. The regulatory architecture simply does not have a framework for what transatlantic dust transport delivers. This is not a conspiracy of regulatory neglect. It is the straightforward consequence of a regulatory system built during a period when transatlantic dust transport was not recognized as a public health issue in the United States, when the biological fraction of that transport had not been documented, and when the monitoring technology for real-time precipitation and chemistry analysis was not available. The Clean Air Act was passed in 1970. Griffin's first papers documenting viable transatlantic biological transport were published in 2001. 30 years of regulatory development occurred before the scientific documentation of the biological hazard existed. Regulatory frameworks are not retroactively updated when new science documents new hazards. They are updated through advocacy, petition, scientific advisory processes, and political will that work on timescales of decades. The atmospheric modeling gap is equally fundamental. The global atmospheric chemistry models used for air quality forecasting, the NOAA GFS Chem model, the Copernicus Atmosphere Monitoring Service in Europe, NASA's Geoscheme, include mineral dust as a modeled aerosol species. They can forecast when and where Saharan dust will arrive in the United States with reasonable skill, as NOAA demonstrated publicly during the Godzilla event when forecast products showing the plume's transit across the Atlantic were widely circulated. But these models treat dust as a single component aerosol. They forecast the mass concentration of mineral dust without simulating the biological fraction, without the iron solubility transformation that Baker and Jickles documented, without the photoprocessing-driven ROS generation that Gracian's laboratory established, and without any representation of the nucleation and below-cloud scavenging concentration mechanisms that make wet deposition a categorically different exposure pathway than dry deposition. A model that forecasts dust arrival as a PM 2.5 event but does not simulate the wet deposition concentration mechanism cannot tell a community that the rain they are about to receive carries 40 times background iron concentration. The forecast skill is real, but the health-relevant output is missing. What the community receives is a forecast of orange haze and reduced visibility, not a forecast of the chemical and biological content of the afternoon thunderstorm. The treatment of the biological fraction in atmospheric modeling is essentially absent. There are research models exploring the atmospheric transport of microorganisms. The bioprecipitation hypothesis that Sands proposed has motivated modeling work, but none of this has been operationalized into the forecasting products that NOAA, the NWS, or the EPA issue to the public. The gap between what the science knows and what the operational modeling communicates is widest precisely in the domain of the biological fraction, the domain that Griffin and Kellogg identified as a public health concern in The Lancet in 2006, nearly 20 years before any operational forecasting product communicated it to communities in the Plume's path. This investigation has documented 3 categories of evidence: the chemical payload of transatlantic Saharan dust and its transformation in transit, the biological payload and its survivability, and the wet deposition concentration mechanism that delivers both to the surface in precipitation. The honest intellectual task now is to present the range of defensible interpretations of what that evidence collectively means for the communities in the Plume's path, without the false certainty of alarm and without the false comfort of dismissal. The most benign interpretation of the available evidence is this: the chemical and biological concentrations delivered by transatlantic dust events, even accounting for the wet deposition concentration mechanism, remain below the threshold of acute health concern for the vast majority of healthy adults in the exposed population. The Canary Islands epidemiological studies show an 8 to 12% increase in respiratory emergency visits on high dust days, a real effect, but a modest one in absolute terms, and concentrated in populations with pre-existing respiratory vulnerability. The viable Aspergillus fumigatus spores arriving in transatlantic dust are arriving into environments where the organism is already present as part of the ambient fungal ecology. The additional spore load from a dust event may be indistinguishable from baseline exposure for healthy immune systems. The pesticide residues and heavy metals, while detectable above background during dust events, are at concentrations that the body's normal detoxification capacity can manage in acute exposures. Under this interpretation, the primary public health action required is better communication to sensitive populations, those with respiratory disease, the immunocompromised children, about the advisability of avoiding outdoor exposure during documented high dust events. The intermediate interpretation incorporates the monitoring gap as a material uncertainty that changes the risk calculus. We do not know the actual chemical and biological concentrations delivered to the surface by the wet deposition pathway, because no monitoring system measures them in real time. The studies documenting 40 times background iron in Florida rainwater and the characterization of blood rain chemistry from European sampling programs represent the available evidence for wet deposition chemistry, but they are not a comprehensive surveillance dataset. The intermediate interpretation holds that the health consequences of wet deposition events, specifically for the sensitive populations in high exposure regions like Puerto Rico, the Caribbean Basin, and the Gulf Coast, are likely greater than the current epidemiological literature documents, because the literature is built primarily on the dry deposition pathway and cannot capture the wet deposition signal in the absence of monitoring infrastructure for it. Under this interpretation, the primary public health action required is the monitoring investment that would resolve the uncertainty. A network of event-scale Gavre precipitation chemistry samplers, sited in high-exposure regions, with biological as well as chemical analytical capacity. The most concerning interpretation acknowledges that the trend documented in the Ridley et al. Satellite analysis, increasing Saharan dust emission over the satellite era, is operating alongside the increase in transatlantic moisture transport and convective precipitation intensity associated with large-scale atmospheric warming. More dust arriving in the atmosphere over the Gulf Coast and southeastern United States, intersecting more intense convective precipitation systems, delivering a chemical and biological payload whose wet deposition concentration mechanisms are not represented in any operational model, into communities whose baseline vulnerability, childhood asthma in Puerto Rico, elderly cardiovascular disease on the Gulf Coast, is already elevated. Under this interpretation, the compound trajectory, more dust, more intense precipitation, no monitoring, represents an escalating public health hazard whose consequences are currently invisible in the surveillance data because the surveillance data is not designed to detect it. The antibiotic resistance gene transport in this interpretation warrants particular attention. a mechanism that annually deposits resistance genes from African agricultural soils into American soils and water systems, repeated across decades as dust transport volumes increase, represents a potential contribution to the antibiotic resistance crisis that has not been studied and cannot be quantified without the monitoring infrastructure that does not exist. What would distinguish between these interpretations? Event-scale precipitations, chemistry monitoring in high-exposure regions, with biological analytical capacity across multiple annual Saharan dust transport seasons, correlated with emergency department surveillance data stratified by precipitation events rather than air quality index readings. That is the specific data collection that the intermediate and concerning interpretations depend on, and that would either confirm or refute their significance. That study has not been conducted. The monitoring infrastructure required to conduct it does not exist. The regulatory and funding framework that would build it has not been invoked. And in the absence of that data, the three interpretations remain equally consistent with the available evidence, which is itself a finding of a specific kind. Strip it to the confirmed record. What we know with certainty about the transport mechanism: approximately 180 million tons of Saharan dust cross the Atlantic annually in normal years, with the June 2020 Godzilla event carrying approximately 25 million tons in a single transport episode, the largest in at least 50 years of satellite records, documented by Dr. Pablo Mendez Campos and characterized by NASA MODIS. The Saharan air layer transports this material at altitudes of 5,000 to 15,000 feet above the marine boundary layer on the trade wind system. Satellite-era analysis by Ridley and colleagues documents a 15% increase in North African dust emission since the early 1980s. The 60-year Barbados monitoring record, maintained by Dr. Joseph Prospero, documents multi-decadal variability driven by Sahel drought conditions, with the most recent decade showing a renewed increasing trend. What we know with certainty about the chemical payload: heavy metals including lead at up to 32 nanograms per cubic meter during heavy events, arsenic, cadmium, mercury, and chromium, documented at the Barbados station by Prospero and colleagues. Organochlorine pesticide residues, including lindane and DDT metabolites, documented in transatlantic dust by Garrison et al. In 2006. Iron solubility increased from 0.1% at source to 5 to 10% after transatlantic processing, documented by Baker and Jickles. Reactive oxygen species generation increase in photoprocessed dust relative to source material, documented by Rubising Hege and Gracian. What we know with certainty about the biological payload: viable bacteria and fungi, including Aspergillus species, documented in transatlantic dust samples in the U.S. Virgin Islands by Griffin and colleagues, with approximately 60% viability for culturable bacteria. UV shielding mechanism for biological survival during transit, documented by Kellogg and Griffin in The Lancet in 2006. Antibiotic resistance genes detected in transatlantic dust samples by Acosta Martinez and colleagues in 2020. What we know with certainty about wet deposition: Saharan dust particles are highly efficient ice nuclei and cloud condensation nuclei, nucleating ice at temperatures as warm as minus 15 degrees Celsius per Atkinson et al. In Nature in 2013. The nucleation and below-cloud scavenging processes concentrate dust's chemical payload in precipitation relative to dry deposition. Iron concentrations in Florida rainwater during the July 2020 post-Godzilla period measured at approximately 40 times background, documented by University of Florida sampling. European blood rain events in Spain document pH as low as 4.5 and metal concentrations 10 to 100 times background in dust-contaminated precipitation per Avila and Guyot. What we know with certainty about health consequences: respiratory emergency visits in the Canary Islands increased by 8 to 12% on high dust days per Perez et al. All-cause and cardiovascular mortality in Madrid shows a 24-hour lag elevation following dust concentration at peaks per Jimenez et al. Asthma-related hospital admissions in the southeastern United States are elevated on high African dust transport days per Reese et al. Puerto Rico's childhood asthma prevalence of approximately 25% positions it as a particularly vulnerable frontline exposure population. What remains genuinely uncertain, the health consequences specifically associated with the wet deposition of pathway, in the absence of event-scale precipitation, chemistry monitoring with biological analytical capacity, whether the antibiotic resistance gene deposition from transatlantic dust represents a meaningful contribution to resistance spread in receiving environments, the quantitative relationship between SAL dust concentration during Gulf Coast convective seasons and the chemical and biological content of resulting precipitation, whether the increase in Saharan dust emission documented in the satellite era represents a sustained long-term trend or a multi-decadal fluctuation. What is unknown and currently unmonitored, event-scale precipitation chemistry during Saharan dust storm, intersection events across the Caribbean and Gulf Coast, viable microorganism concentrations in precipitation during dust events, real-time dust chemistry characterization beyond PM2.5 mass concentration in the ambient monitoring network. The regulatory framework that would fund and mandate any of these monitoring capabilities does not exist. What this channel will continue watching, NASA MODIS and the Copernicus Atmosphere Monitoring Service dust transport forecasts, which are publicly available and provide advanced indication of major plume transport events. NOAA's Saharan air layer, analyses during the Atlantic hurricane season, which track SAL position and intensity with daily updates. Any development in the EPA's regulatory consideration of Saharan dust as a distinct aerosol type requiring specific monitoring protocols, a conversation that has occurred at the margins of the regulatory literature but has not entered the formal rulemaking process, and any peer-reviewed publication that addresses the wet deposition pathway directly, the specific gap that makes the intermediate and most concerning interpretations of the available evidence irreducible at present. There is rain falling somewhere along the Gulf Coast right now, or in the Caribbean, or over southern Florida, the kind of afternoon convective rain that characterizes summer in those regions and that most people shelter from without a second thought. Whether that rain is chemically and biologically ordinary, or whether it carries the iron oxides and pesticide residues and viable fungal spores of the Saharan floor 4,000 miles to the east, is a question that no federal agency can answer in real time, not because the science to answer it doesn't exist. It does. Not because the analytical methods don't exist. They do. But because the monitoring infrastructure that would apply that science and those methods to the rain falling on those communities has not been built. That is the finding this investigation returns to consistently across everything it has examined. The dust is real. The chemical transformation during transit is real. The biological fraction is real. The nucleation concentration mechanism is real. The health consequences, 8 to 12% more people in emergency rooms on high dust days, are real and published. What is not real is the connection between that published science and the public communication and monitoring systems that would allow the communities underneath the plume to know what is in the rain they are standing in. Before closing, address the question of scale and agency honestly. The Saharan dust transport system is not caused by any human action in the direct sense. It is powered by the thermal engine of the world's largest desert and the trade wind system that has been moving that material across the Atlantic for millions of years. Saharan dust arrives in the Caribbean regardless of any decision made by any government, any corporation, or any individual. That is not the framing of conspiracy content, which attributes it to human agency. It is the framing of atmospheric science, which documents it as a natural process. But natural processes interact with human decisions in ways that determine how much damage they cause. The Sahel land degradation that has expanded the available dust source area over the last century is a human-influenced process, the consequence of agricultural intensification, deforestation, and population pressure in a region where the relationship between vegetation cover and dust emission is direct and measurable. The Barbados records documentation of the correlation between Sahel drought and Atlantic dust transport is also the documentation of a human decision landscape. Land use choices in the Sahel that left soil bare when the drought came, amplifying the dust signal far beyond what pure meteorological forcing would have produced. The restoration of Sahel vegetation, already partially underway through the Great Green Wall Initiative, a Pan-African effort to restore trees and vegetation across the Sahelian belt, is a human decision with a direct and quantifiable effect on the volume of material entering the Atlantic transport system. The monitoring gap is entirely a human decision. Every element of the monitoring infrastructure that would resolve the uncertainty in this investigation, the event-scale precipitation chemistry samplers, the biological analytical protocols, the regulatory framework for transnational aerosol transport as a public health issue, exists as technology and as science, as it exists as a peer-reviewed case made repeatedly by researchers like Griffin and Prospero, who have spent careers documenting the phenomenon. It does not exist as funded deployed operational infrastructure. That is a choice made through the accumulated weight of budget priorities, regulatory frameworks, and institutional attention horizons that treat transatlantic dust as an air quality curiosity rather than a compound chemical and biological public health issue. Dr. Griffin has been publishing peer-reviewed documentation of viable biological transport in transatlantic dust since 2001. In more than 2 decades since those first papers, the phenomenon has been reproduced, extended, and confirmed in the scientific literature. The antibiotic resistance gene dimension was added to the picture in 2020. The regulatory and public health frameworks in the most affected U.S. regions, Puerto Rico, the Gulf Coast, Florida, have not been updated to incorporate any of it. That is not a conspiracy. It is a failure of the translation mechanism between scientific knowledge and public health policy that operates in this country and in every country with a comparable regulatory structure. Science produces findings. Findings require advocacy, policy engagement, and institutional attention to translate into monitoring programs and regulatory frameworks. The advocacy required to build a monitoring network for transatlantic dust precipitation chemistry has been made in the peer-reviewed literature for more than 2 decades without generating the institutional response that would fund it. The rain is falling. The plume is coming. NASA's MODIS instrument is tracking it across the Atlantic right now, producing daily dust transport forecasts that show its position and intensity in detail. What it is carrying, chemically and biologically, and what that means for the communities in its path when the afternoon thunderstorms pull it down into the rain. That is the question this investigation has built the case for answering. We will be watching. We will be in the forecast products and the peer-reviewed literature and the monitoring data as it comes in. And when the monitoring infrastructure that this investigation has argued for is built, if it is built, we will tell you what it finds. The plume does not wait, and neither do we.